I always ask you if you have any questions before class, just in case. Those of you who had me before know that. You get sick of hearing it, but I always want to make sure that you have a chance. All right, so pretty much today what I want to do is I want to completely wrap up all the biology that we're going to talk about, and I hope to sort of start sliding into the Markov chain stuff. We'll see how it goes. But in any event, we've talked about how, first lecture we talked about cells and what they did and all that stuff and the information flow and all that. And last time we talked about reproduction, so how eukaryotic organisms reproduce. At least part of that story, okay, part of the story, at least what we talked about was how the parent genotypes, and remember we talked about sexually reproducing organisms rather than asexually, so we have to have two parents for every offspring, determine, and I'll put that in quotes because there's a lot of randomness that comes in here, the offsprings. Actually, let me use the word genome. I haven't used the word genotype yet, so genome. Okay, so that's just one piece of the reproduction story, but it's an important piece. And the kind of randomness that happened here, like crossover, when you're forming germ cells, say, in a diploid organism, or when you're just making the genome for the offspring in a haploid organism, or point mutations, those sources of randomness are important, but they are well modeled. That's the best modeled sources of randomness in biology / evolution / whatever. Okay. So now what I want to do is now I want to talk about sort of the big picture evolution. Okay, sort of like a bigger picture than what we've talked about so far. And you'll see that there's a lot of sources of randomness here that we don't really have good models for, and yet all the kind of mathematical work that people do modeling evolution and using evolution as inspiration for genetic algorithms or evolutionary game theory, whatever, it completely bleaches out a lot of the complexity and settles on some kind of simplified model of the randomness that's going on. You'll see what I mean by that. Okay, so first of all, we have to get a grip on the concept of a population of individuals. And by the way, in biology, time is continuous, so time in real life is continuous. But what we're going to do, just for the purposes of this discussion, is pretend it's discrete. So it just clicks along in increments of integers and all that kind of thing. As you'll see. And what we're going to do is we're going to consider a situation where you have a population at time t, a population at time t plus 1, a population at time t plus 2, and so on for all possible times. So for each integer time t, I'll put time in quotes because you could think of whatever, time t, you have a population that I'm going to call population at time t, call it capital P of t. Okay, so what is a population? What does that mean? For each t, P of t is, it's a set of what we call individuals. And it's actually somewhat different from what we'd ordinarily think of as a set, and I'll talk about that in a while in a little more detail. But essentially, it's a set, or more accurately, a multiset, I'll tell you what I mean by that in a second, of what we call individuals. Okay, so what is an individual? You can think of each individual as just an entity that has a type. Okay. And it's an entity fully determined by its type. And what is its type going to be? The type of an individual is a pair that I'm going to call little g, comma, little phi. Okay? Where g is what we call the genotype of the individual, and phi is what we call the phenotype of the individual. So g is the individual's genotype, and the genotype here just means the individual's somatic nuclear DNA genome, whatever we've been calling it. So genotype, that is to say its genome, its nuclear DNA, somatic nuclear DNA. And phi is the individual's phenotype. What is a phenotype? I'm not going to be too careful about defining what the phenotype is in some kind of mathematical sense or tell you what kind of set phenotypes belong to. Just think of it as a summary of some kind of summary of all the traits of the individual that are relevant to determining whether it reproduces. Okay, so think of this as some kind of summary. I'll put that in quotes. And when I talk about the really stripped down models of evolution that people consider sometimes, you'll see this manifest itself as like a vector of trait values, whatever. But you'll see that in a little while. As some kind of summary of the traits, the individual's traits, that are relevant to whether it, and I'll be neuter when I talk about individuals, I won't say he and she and all that kind of thing, reproduces. Okay. So you can think of an individual as a pair G phi if you want, but it's probably better to think of an individual as an entity that has a type given by a pair G phi, and think of different individuals as having possibly the same type, possibly the same G and phi, or possibly the same G but different phis, possibly the different G's and the same phis. So note, in a population, different, let me just say it really carefully here, two different individuals can have the same type or the same G but a different phi. And we talked about that last time, the whole idea that when you have a genome that does not determine the organism, even though Vinay said, wait, don't two people who have the same genome, aren't they the same? No, they're not. Okay, they're not. Because the genome is a recipe. It's not a blueprint. And how that recipe gets implemented depends on, yeah, Andrew. Oh, redirect, yes.
I thought that, I was just going to say that, isn't the phenotype dependent on the genome?
It depends on it, but you'll see the mapping is both one-to-many and many-to-one. I'm going to talk about that in a second, okay? Okay, so just hold that thought. You can have the same genome but different phis. And you could also have different genome but the same phis, because the differences in the genome might not affect any of the traits that are relevant to reproduction. That's something that sometimes you don't think of. You know, like there might be something in the genome that has no effect on anything that would have any effect on whether the creature gets to reproduce. Okay. Now, the reason I said more accurately a multiset is that even if you think of it as a set of individuals, you can think of it for this reason as a multiset of types. So what is this idea of a multiset? A multiset is kind of like, suppose you can have, say, two different types of individuals. Say one of them is capital A and one of them is capital B. Okay. Let's write down a couple of populations just listing the types of individuals in the population. So here are a couple of populations. A couple of populations of individuals with these possible types. Here's one. It's like A, B, B, B. And how about A, A, A. All individuals are type A. Or how about A, B, B. These guys we think of as the same. We don't care what the order is, the way we list them. But the point here is that different types can appear multiple times in a given population because you might have several individuals with the same type. And this kind of a thing where you have the same thing several times possibly inside of a set sign is called a multiset. So a multiset is equal to sort of like a set where multiple things, multiple copies of the same thing, and I'll put same thing in quotes because, you know, if it's multiple copies then they're different things, but it's the same thing, you know, essentially up here. Okay, so that's this multi-set idea, and we'll see a lot more of this when we talk about, you know, genetic algorithms and all that. Okay, and we think of our populations as unstructured in the sense that there's no concept of neighbors, nearest neighbors, or anything like that. No sort of graphical structure on the population, which is why this one and this one are the same, even though I've listed the A's and the B's in a slightly different order in those two. In both cases, I have a population with 2 A's and 3 B's. We think of those as the same. So there's no sort of quote-unquote nearest neighbor type idea. And above you see sort of 2 renderings of the same population, quote unquote 3 A's, or is it 3 B's? 2 A's and 3 B's. That's the only thing that's relevant about the population, is how many A's there are, how many B's there are. Okay. All right, so that's what I mean by a population. It's a set of individuals, or you can think of it as a multi-set of types, whatever you want to think of it as. Each individual has a G and a phi, a genotype and a phenotype. Now, you asked this question a few minutes ago about, wait, doesn't the phenotype depend on the genotype? Sure, absolutely it does. Absolutely it does. But it doesn't depend on it in a simple way. Okay, so how are G and phi of a given individual related? Well, phi is the recipe, or sorry, G is the recipe for phi. But what phi arises from a given G depends on lots of things, lots of random effects. And I'm going to indicate that by drawing a really curly arrow, and I'm going to put a delta over that arrow to indicate that there's a lot of random effects that, taken in concert with what G is, determine what phi is. So the curly arrows and these things, these pictures, curly arrow indicates, quote unquote, lots of random effects coming in. Now, what does this letter delta stand for It stands for development. If you have a genome, it develops into an adult. It develops into a phenotype. The process of development is not well understood. I mean, some aspects of it are, but some aspects of it aren't. Like how, for example, like last time I mentioned, as we all know, everybody comes from one cell to start with. How does that cell sort of decide, okay, after dividing for a while, you guys go and become a liver, you guys go and become a brain, whatever. How do cells differentiate? All these tiny little asymmetries and chemical imbalances and all that kind of stuff lead to cell differentiation and the immense complexity of the phenotype, the adult organism. It's crazy. People don't really understand what happens, and there's lots of random effects that come in here. These random effects include simple environmental effects. Like, for example, what kind of diet? If it's a mammal, say, so it's a mother carrying a baby or carrying a whatever, fetus, what kind of diet does this mother eat while pregnant? That's like an environmental effect that affects the development of the G into the phi. But there's lots of other kinds of random effects. There's lots of other kinds of random effects. There's way too complex to model completely. And this delta is not really a mapping. And this is trying to answer your question a little while ago. Delta, in this sense, is not really a mapping in a set theoretic sense. That is to say, G does not determine phi. So the G to phi correspondence is both one to many. For example, if you have two identical twins, they have the same G, but they have different phis, right? Okay. And many to one. As I indicated earlier, the G might contain some things that give rise to nothing that's phenotypically relevant. Nothing relevant to whether the individual gets to reproduce. Okay? Now, in the stripped down models we talk about a little later, we'll see this delta in one case is actually a one-to-one mapping with no random effects at all. And that shows you right away how things get assumed away in order to do math, which is what we do all the time in engineering and science, but whatever. I'll save that up. All right, so this is one thing. Now I'm going to introduce a little bit of notation, and I hope this won't get too heavy. I don't think. At least I don't think it's too heavy. And I hate these noisy erasers. This is a much quieter eraser. Okay, so anyway, a population of time t is a set of those kind of pairs. So summary so far, P of t is a multiset of G comma phi pairs, each corresponding to one individual in the population. All right, for each t, what I'm going to do is I'm going to let Pg of t be the multiset of genotypes of individuals in P of t. So all you do is you go through this big list of these G phi pairs, and you just pluck out the G's and you throw them into a set. And you might get the same G twice or 3 times or 4 times because of the multisetness of P of t. Therefore, Pg of t itself is a multiset, not just a set. And P phi of t is the set of phenotypes. the multiset of phenotypes of the individuals in P of t. Okay? Just for the heck of it, so introduce those notations. Okay, so question, how does the, now we know how genotypes lead to phenotypes by this crazy random, how does the population at time t give rise to the population at time t plus 1? Let's consider that. So how does P of t give rise to P of t plus 1? Well, I'm going to assume the following stripped-down model, that some subset of P of t reproduces, some set doesn't reproduce, and once that's happened, everybody who doesn't reproduce dies, and the new population is just the offspring of the ones who did reproduce. Okay, so here's a stripped down. Everything is stripped down when you try to get mathematical about this stuff. So here's a stripped down scenario. Some subset, let's say R of t of P of t. And when I say subset here, I mean sub-multiset. R of t can have the same, have repetitions in it. Some subset R of t of P of t reproduces at time t to give us P of t plus 1. And everybody dies, the offspring of this set constitute P of t plus 1, and everybody else disappears. So R of t, those guys disappear. Everybody in generation t disappears, and the only thing left over is the offspring of P of t plus 1. And I'm not going to worry about whether one guy in R of t has 10 offspring or 3 offspring or whatever. I'm not going to fix it to be 1. Just think of it as some subset reproducing and giving rise to the following population. What subset reproduces? You can think of R of t as arising from P of t by means of another kind of heavily randomly encumbered process. So let's say P of t together with lots of weird random effects, and I'm going to call this correspondence capital sigma, gives rise to R of t. Okay? And what does sigma stand for? What do you think sigma stands for? If delta stood for development, what's sigma going to stand for? Selection. Excellent. Who said that? Good job. Okay. Sigma equals selection. Now this is kind of a deceptive word. And, we're going to have I'm going to have a lot of sermonizing to do about this momentarily. But the point is, once again, lots of random effects enter in that are too complicated to model. Like for example, like what's the environment? If it's really cold and you have some individuals who are sensitive to cold and they die at age 15 before they get to reproduce, because of that environment, that's going to be different from if it's a warm environment. Those guys might live. There's things like that. But there's lots of other things too that come into the selection process. Now, what's really important, there's one thing I want to say generally, that sigma, this selection process, only operates on the phenotypes of the guys in P of t. It doesn't sort of see the underlying genotypes. So generally, we think of this sigma as only caring about P phi of t, not about P g of t. In other words, the only things that affect whether, the only things about an individual that affect whether it gets to reproduce are its phenotypic traits, not its genotypic traits. Or not its phenotype, not its genotype. Phenotypic trait is kind of a, well, it's not quite redundant, but whatever. Okay. Now, what's maybe the most famous phrase you ever heard when, you know, in a sort of a cocktail party level conversation about evolution? Like, what determines whether someone gets selected to reproduce? Well, natural selection, that's a good phrase.
The strong will
Michael.
survive.
And a variation on that, the strong will survive. Survival of the fittest. Survival of the fittest. Yeah, very, very close. Okay, now that is a really deceptive phrase. It's a really deceptive phrase. Okay, so here's a deceptive phrase. And here's where the sermon starts, okay? Quote unquote, survival of the fittest. Survival of the fittest. That is to say, who gets selected depends on how fit they are. So I don't even have to elaborate on that. Now, what kind of picture does this conjure up? It conjures up a picture of the following kind. And of course, being an applied mathematician, I have to phrase it mathematically. Let capital phi equal the set of all possible phenotypes. There's some function, let's call it f for fitness, a real valued function on phi. And for those of you who didn't take ECE 3250, your loss. No, just kidding. This is this is a symbol, meaning f is a mapping from phenotype space to the reals. It takes every phenotype and assigns it a real number. And let's call that real number the fitness of the phenotype. So there's a function, f from phi to r, where f of any little phi is equal to the fitness of phenotype phi. And whether a phenotype gets selected to reproduce depends on some random effects together with the value of its fitness. Okay? So whether an individual with phenotype phi gets to reproduce, that is to say, lands in capital R of t, the set of all individuals that get to reproduce depends mod some randomness on the value of its fitness. Okay, now when we talk about genetic algorithms, we'll see that this is actually how they do it mathematically. But in biology, this is all wrong. This is completely wrong. It's completely wrong. It's wrong for two reasons, at least. So this is wrong for at least two reasons. Okay, reason one. And to me, this is in some sense the most important one. Survival of the fittest, that phrase, is really a tautology. And I'll put SOTF like, have you guys noticed, like, the last 10 years or so was the first time I ever noticed people using, like, POTUS, SCOTUS for President of the United States, Supreme Court of the United States. Now they're using SOTA for, or SOTU for State of the Union, right? That happened this week. Anyway, survival of the fittest is a tautology. Everybody know what a tautology is? It's like A if and only if A, right? Survival of the fittest is a tautology in this sense. In bioevolution, and this is a mantra that echoes through my mind 24/7. Seriously. Individuals don't survive because they're fit. Individuals are deemed to be fit because they survive. You can only define fitness evolutionarily in the rearview mirror. There's no fitness function, there's no F on phenotype space that linearly orders phenotypes with respect to fitness. That's why survival of the fittest is a tautology. The second reason is, the second thing is, that's wrong with this mathematical picture is that this F that we're talking about here, this F is what one would call an exogenously defined fitness function. So the F in the picture above presents an exogenously, and this is an important word. Let's just say exogenous. Stephen King said the road to hell is paved with adverbs. So let's try to stick with adjectives. No, it's seriously a way to weaken your letter of recommendation. Say I'm writing a recommendation for somebody for like a grad school, like Drew. I wrote him a recommendation this year. I took out all the very's. Like I put very here and there. No, I get rid of that. Get rid of all that. Because it sounds so much better without the adverbs. It really does. Okay, so anyway, this picture presents an exogenous fitness function. Exogenous means one that comes from the outside. And I'm not talking at all about, gods or anything like that here. I'm just, this is pure math we're talking about here. Quote unquote, comes from outside. But in biology, in biological evolution, whether someone is fit, that is to say, whether they survive, doesn't depend just on exogenous factors like the weather or whatever else. It depends on who else is in the population at the time. It's an endogenous thing. So in real life, who survives in P of T? And I'm using the word survive here as sort of an abbreviation for who gets selected to be a member of R of T, the reproducing members of the population. Who survives in P of T depends not just on external factors, for example, the environment, but on who else is in the population. And just to strip it down to its most elementary form here, this is actually where game theory comes in. This is where game theory comes into the whole discussion of evolution, because game theory is about situations where what happens to you depends not only on how good you are, but on what everybody else is doing. Okay? So this is sort of the entry point for game theory. So anyway, I always forget the last word, so I don't know where to pick it up. But on who is in the population. That is to say, fitness is endogenous. So this is endogenous as opposed to exogenous. But we say endogenous and exogenous because it sounds more British. Okay, and this is where game theory comes in. And let me just give you a really simple example. And this is one where I use a terminology. I use terminology that's unconventional, I think. Okay, you've all heard of the game where, you know, you go 1, 2, 3, boom, and you either do this, this, or this, right? Is everyone watching? This, this, or this, right? Okay, what do you call that game? How many people call it rock, paper, scissors? How many call it something else? How many have never heard of it? Okay, I call it scissors, paper, rock. I'm sorry. Okay, now, somehow I think it's more positive to call it scissors, paper, rock, because scissors beats paper, beats rock, whereas you're calling it rock loses to paper, loses to scissors, right? So, a classic child's game is scissors, paper, rock. What?
Did you make your friends say it that way?
I don't ever make my friends do anything. No. Sometimes they do it just because they, you know, they respect me or something. But same thing with you guys, right? Okay, so anyway, a classic game. Okay, how fit is a scissors? Answer me that question. Phenotype space is SPR, right? Those are the three possible phenotypes. Now let's try to find a function that describes the fitness of these three phenotypes. Can you come up with one? Let's just normalize it so f of s is equal to 1. No, you can't, right? Because depending on who else is there, scissors might be really fit, or paper might be really fit, or rock might be. Like, if I'm one scissors in a population of papers, I'm extremely fit. You know, like, there's nobody to crush me, there's no rocks, and I have lots of food, right? Okay? If I'm in a if there are 49 scissors in one paper, well, scissors is still kind of fit because there's no rock to crush him, but there's only this one paper for everybody to split to eat, and so how fit are you if you're going to have to eat like 1/50th of what you need, you know, that kind of thing. If you have a population of all scissors and rocks, the scissors are toast. They're completely unfit, right? So just that picture, that simple picture, ought to give you an idea of how fallacious that F from phi to R model is, in terms of at least biological evolution. And why fitness has to be defined endogenously. All right, so anyway, that's the sermon. And I guess is that a good time to do a 2-minute break? Yeah, or a 3-minute break. Let's do the break now, and then I'll continue talking about this stuff. The selection thing to admire, not to nail it down. It's lots of random effects, determine who gets to reproduce, and we already discussed in some sense how the reproduction occurs. So finally, once you have R of t, well, it's not quite finally, so let me just say once you have R of t, anyway, once you have R of t, you can define R phi and RG similarly to how we define P phi of t and P g of t. In other words, Rg is the set of all genotypes of individuals in R of t. R phi is the set of all, or multiset or whatever, of all phenotypes in R of t. And it turns out that the population at time t plus 1 arises first by Rg determining the genotypes of the folks in P of t plus 1 by means of the reproduction process that we talked about last time, with whether it be crossover or meiosis and crossover and whatever, like mutations. So Rg of t, quote unquote, determines Pg of t plus 1 via the kinds of processes, crossover, mutation, etc., that we discussed already. And we noted that those processes were a source of randomness, and that randomness is the best understood randomness in biological evolution. It's better understood than the randomness that attends delta and the randomness that attends sigma, but it's still random. So we have a similar curly arrow picture. That looks like this. R of t gives rise, subject to a bunch of random effects, by something I'm going to call gamma, capital gamma, to Pg of t plus 1. Okay. What do you think gamma stands for? Game? I wish. How about genetic operators, whatever? And the same way that sigma depends only or cares only about P phi of t and not about Pg of t, gamma, quote unquote, cares only about Rg of t and not R phi of t. It doesn't give a hoot what the phenotypes of these things are. It just cares what their genotypes are. All right. And now we're back to the set of genotypes of some population, and we know how the phenotypes arise from that by this process of development. So here's a summary picture. Population at time t. Some subset of that gets selected, and you get R of t, and this cares only about P phi of t. Then those R of t's get together, or whatever they do, mix their genomes through a random process gamma. This cares only about Rg of t, not R phi of t. And that gives you Pg of t plus 1. And now you have genotypes for the next population, and they all grow up by means of this incredibly complex process of development to give you P of t plus 1, the set of all individuals in population at time t plus 1. And all the curly arrows indicate that there's lots of random effects that are occurring. All right, so that's sort of the big picture of how populations evolve. And I want to talk about some stripped down, completely false in terms of science, but useful in terms of developing intuition, things that people do to simplify this. And I'm just going to talk very briefly about 3 of them. Okay, so here are three completely incorrect, scientifically inaccurate, but conceptually useful. I'll put that in quotes because it's a value-laden term, and there might be a subset of the class who comes up to me and says, you know, these are absolutely useless. I don't know why you characterize them as useful, you know, whatever. Useful for me, okay. Scientifically useful oversimplifications. And the first one is one that's really an oversimplification, and it's completely wrong in obvious ways. And that's called, and it only has, as far as I know, there's no name for this except the following pejorative name, beanbag genetics. Okay, so that's a pejorative name. That's clearly a name that someone who's criticizing a theory or a model is going to call it something like that. And it's pretty obvious why when you look at it. Okay, in this setup you model G and phi for an individual, and that's for all individuals, as vectors, finite vectors of the same size. So there's, say, a 50-dimensional G and a 50-dimensional phi. And you think of the individual entries in G as genes. And you think of the entries in phi as traits. Have to learn how to spell traits. And furthermore, the mapping from G to phi is not complicated by any kind of randomness at all, and it doesn't have any kind of many-to-one or one-to-many complexity. It's element to element. So the G to phi mapping is both super simple and non-random in the sense that GI determines phi I for 1 less than or equal to I less than or equal to n, which is going to be the size of G and phi. And I'm using G sub I and phi sub I to indicate the ith entry in G. So in this model, gene determines trait. Gene determines trait. One gene determines one trait, et cetera, et cetera, et cetera. And they're the same number of possible traits as genes. You can't have two genes influencing the same trait or one gene influencing many traits. Not allowed. So this is the delta simplification. That attends this model. What about the sigma simplification? As for sigma, you do define some function f from phenotype space to the reals. An exogenous fitness function that is some kind of appropriate aggregation, perhaps a weighted sum, of fitnesses of individual traits. For example, you could have, like I say, f of phi is equal to some sum from, say, k equals 1 to n of w sub I f, I don't know, something, I don't want to do that. So a sum, or weighted sum, of fitness is the individual traits. And the gamma takes place pretty much the way we talked about last time. You know, with crossover and mutation or whatever on the G's, but respecting the structure of the G's. Okay? Yeah, Matt.
Is that mapping bijective? Like, is there one unique, like, phi of I for each G of I? Or can two map to the same phi?
I hadn't thought about it. Let me think a second. So suppose the G's are real numbers. Is it conceivable that two different G values could give rise to the same value of the trait to which that G corresponds? I think that's possible, yeah. So I don't think so. It's not bijective, I don't think. But GI determines phi I for each I. Each element goes 1 to 1. Now, the point of that you know, you've led me to make here, that I meant to but forgot to mention, might as well mention it now, is that in this sense you can think of the fitness function here, F, because it maps phenotypes to the reals and every phenotype is determined completely by the genotype, you can figure some mapping on genotype space as well. You can talk directly about, quote unquote, the fitness of a genotype. So note, because phi, G determines phi in an individual, which is a pair, G comma phi, and phi determines individual G comma phi's fitness, G determines the individual's fitness. So thus, you can think of this fitness function as operating on genotype space. And that's what genetic algorithms do, essentially. So, and I'll put it this way, you can view fitness of genotypes as a meaningful concept. And this is how it works in standard classical genetic algorithms. In some sense, in fact, it's even more, it is bijective. In that case, it's 1 to 1. And there's an identity between phenotypes and genotypes there. All right, so that's clearly inaccurate, right? It completely bleaches out this magic wand of having G determine phi, gets rid of the whole development process as an interesting complication. The exogenous fitness function gets rid of any consideration of who else is in the population. So you can't have something like SPR going on here. No way. Whatever. So that's one example of an oversimplified model that, and you know, you can play around with the math there. There's non-trivial randomness that comes from the gamma process, and you can develop, you know, use Markov chains, which we're going to be studying to study this kind of a thing. It's not obvious what happens, and as you tweak the various genetic operators like crossover, the kind you allow, the kind of mutations you allow and everything, you get some very interesting math. So I don't want to sort of flush that thing and say that this is not something you'd ever want to think about, even in your sleep or something. So note, because of the gamma randomness, you get some interesting math here. But it's completely useless from a biological standpoint. And I'll put that in quotes, too. So that's one. Yes?
So it's written here that P determines G phi's fitness, right? Individual's fitness.
Yes.
And then G also determines G phi's fitness, right? Like, I don't understand.
G determines phi.
Right.
Phi determines fitness of G phi.
So can we say that G determines fitness of GP?
Yes, that's what I meant to say. Let's see if I said that. Yeah, if someone comes up to you on, this is the first Hope Plaza thing of the semester, okay. If someone comes up to you in the Hope Plaza using a beanbag genetic kind of way of thinking, right, and says, this individual has genotype G. Do you know what its fitness is? What would you do? You would say, well, let's see. I know that I can figure out phi from G, right, because it's a beanbag genetic model. And then I can figure out the fitness of the individual G comma phi from phi. So then I can tell that person what the fitness of the individual is, right? If he just tells me the genotype.
But then it's like 1 to, like many would be an understatement, like wide array, right?
I'm not sure I understand your question.
So see, G determines phi,
Yes.
and that's a 1 to many mapping, right?
No, in this case it's not one to many. It's a mapping. It's a true mapping. GI determines phi. It's a true mapping.
And phi to fitness, is that a 1 to 1 or a 1 to many?
It's not necessarily either, but it's definitely not one to many. See, anything that looks like this is not a mapping, okay? But this is a mapping. Like you could have the same fitness value for two different phis, but you can never have different fitness values for the same phi. You can have the same phenotypic value for two different Gs, but you can't have two different phenotypes for the same G, okay? I can sit down with you afterward and try to explain it better. How about that? Okay. All right, so anyway, that's beanbag genetics. Now, one that's a little bit less useless, okay, is something called gene selectionism. And this is almost a pejorative term, and this is in the manner of Richard Dawkins. You've probably heard of him. He's kind of made a name for himself nowadays as kind of the high priest of atheism and all that, but really he's an ethologist. He's an animal behavior guy, right? And he's spent his whole career at Oxford and Cambridge and everything, and he's written some amazing books on evolution and everything that have nothing to do with religion, whatever. And in fact, one of the best popular science books I've ever read, it's called The Blind Watchmaker, and it was written in the 80s on evolution by Richard Dawkins. But anyway, I'm going to give a stripped down version of what they talk about. And I said this is sort of a pejorative name because it's the kind of thing that people who don't like to atomize things, people who don't like what they call reductionism. Reductionism is an evil word to a subset of the scientific community, and there's sort of a science wars that's going on all the time in various fields. Like, oh, that's reductionist. You're taking something way complex and oversimplifying it. Well, of course you are. That's what you do in science, right? You model things. You do the best you can, you know, and you don't assert. You don't make some. And they accuse Dawkins and company of making all these assertions that they don't make. And I'll try to point out some of those in a minute. And if they're kind of mad at them, they say, well, that's gene selectionist reasoning, right? And if they're really mad at them, they say that's gene selectionistic reasoning. Like if you add an IC at the end of any kind of accusatory adjective, it turns it into something evil. Like, oh, you know, that's a socialist kind of policy. No, that policy is socialistic. See? See, it sounds much more evil when you put in. So I'm not going to say gene selectionisticism. I'm going to say gene selectionism a la Richard Dawkins. Okay, so how does this one go? And how does it differ from beanbag genetics? Well, let's try to keep it in parallel. You model G and phi as vectors. Again. But first difference is the vectors don't necessarily have to have the same size. That's one thing. Okay. Yeah, Matt.
When you say that they do have the same size,
No, no, I mean same number of elements. That's all I mean.
Number of dimensions.
Yeah. Maybe I should put dimension here instead of size. That's what I meant. Like if you have an n-dimensional vector, the other one's an n-dimensional vector as well. That's what I meant. All right, so you have two, not necessarily the same dimension. Okay, so that's the first difference. Okay? And you still, unfortunately, have G determining phi completely. And the way that you justify, the way that Dawkins justifies this is using what people in science and philosophy call ceteris paribus arguments. Okay, so this is justified, and I'll put that in quotes, using what are called ceteris paribus arguments. And by the way, there's a few people who have to leave early for other classes, and they've told me, and if they're leaving, don't worry, I'm not kind of glaring at them saying, like, why are you leaving early or whatever. Ceteris paribus means, quote, all other things being equal. Okay. So this is like et cetera, you know, and other paribus, on a par with, equal with. That's where the Latin comes from. But people call it ceteris paribus arguments. But the thing is that the accusers, the ones who call Dawkins gene selectionistic, always say, he doesn't think development is complicated. Look, he's saying the genotype determines the phenotype completely. No, he's not. He's acknowledging that the world is very complex, but all other things being equal, one can approximate this genotype to phenotype mapping for the purposes of an oversimplified model. All this is hyphenated without worrying about development. Okay, so in some sense what it does is he bleaches out the randomness in development this way, but he allows, and he's not the only one, by the way. This isn't a one-man show. A lot of people think this way. He bleaches out the randomness in delta, but he allows for complexity. Now, if you look over at the discussion of beanbag genetics, the G to phi mapping is both super simple, that is to say it has no complexity at all, and non-random. In Dawkins, in gene selectionism, it's non-random, but the randomness is acknowledged politely. But it is possibly very complex. The G to phi mapping can be very complex. And it's certainly not element to element. In fact, GI determines phi wouldn't make any sense here, because G and phi aren't necessarily even the same size vectors. They might have different dimensions, right? Now, what are the kind of complexities that arise in a G to phi mapping that's allowed to have complexity but not randomness? There's two really important ones. So the complexity here, the complexities allowed include, and I'm using this sort of as an excuse to teach you guys a couple words. One word is pleiotropy. Does anyone know what that means from biology? Trevor, you seem to be the bio expert. That might be something like what? Well, that's the next one. Yeah, you're right. It's the other direction of that. Pleiotropy is one gene, one element of G can influence many elements of phi. So one gene element of G, thought of as a vector, can affect multiple traits, elements of the phi vector. And polygyny, or polygyny, or however you want to say it, many genes can affect one trait. So, for example, a very simple way that the G and the phi might depend on each other might be linear. Like you might have say, phi vector equals some matrix, call it M times the G vector. So this is a matrix. It doesn't have to be a square matrix because phi and G might be different sizes. It'll be whatever size it has to be to make that equation work. And if M has rows that have non-zero elements all the way across, that's this polygyny thing, that many genes, many elements of phi affect one element of phi, G affect one element of phi, and if it has columns that have lots of non-zero things in it, that means one gene, whatever gene hits that column when you do the matrix multiplication, affects all the different traits. So as long as M's not diagonal, so highly quote-unquote non-diagonal, then you're going to have pleiotropy and polygyny. All right, so I'm just trying to emphasize here that this model, albeit a very simple one, and albeit argue away the randomness using ceteris paribus stuff, does acknowledge the randomness and does allow for a complex relationship between genes and traits, much better than beanbag genetics. Okay, now in this case, how does the selection work? We saw how the selection worked for beanbag genetics. We had this exogenous fitness function. And Dawkins would never sit still for anything like that. Okay, so what about selection? Here, in this gene selectionist paradigm, it's certainly not any kind of exogenous fitness function. So the endogeny, that's the noun form of endogenous, of selection is acknowledged. Okay? And he does this useful analogy that I can't write enough in 2 minutes to describe it to you on the board today, but I'll describe it to you next time. But think of it this way. Okay? Has anyone here ever, I can tell by looking around the room, the answer is no. But have you ever been on a crew team? Okay, ha ha ha, you say. Well, last time I taught this course, I had Sam Odell and Mark Hendrick in my class, and they were both rowers. Okay, so there. So it is possible for rowers to take EC 4271. Anybody, any of you know either of those guys? Yeah? Sam and Mark? Okay. Anyway, suppose you have an 8-person, or let's not worry, 8-man boat, okay, in a crew race. There are different seats in the boat, right? And the different seats generally have different specialties. Like the one who sits right next to the coxswain is called the stroke. And he has to be very steady, and pretty strong. And the ones that are right behind him in the boat, remember, everyone's facing the opposite direction. The boat's going this way, but we're all rowing like this, right? And the coxswain's sitting here screaming at the... We're almost done, don't worry. Everyone has a different specialty, okay? So it goes bow is the one who's farthest away from the coxswain. There's 2, 3, 4, 5, 6, 7 stroke. There's 8 rowers in the boat. And you can think of those rowers as like genes, right? And you can think of the boat as the vector of genes. Now what about the phenotype? Well, the phenotype is how good a boat is it, right? So if a coach wants to pick a team, what he or she, I'm not ruling out a female coach for a male crew team, is going to do is something like this. Okay, here are my candidates for 2-seat, here are my candidates for bow, here are my stroke candidates and all that stuff. What I'm going to do is I'm going to randomly assign them to a boat, randomly assign these guys to a boat, you know, according to their seats, and then have a pairwise race, a race one against the other. And I'll give everybody who wins a W and everybody who loses an L. And then I'll just do it again. I'll keep doing that. I'll keep generating random boats, right? And pairing them off, letting them race. And everybody gets a bunch of wins. And sometimes some L's. And so how do I pick my final boat for the regatta? Well, I take the stroke candidate who has the most W's, the 7-seat candidate who has the most W's, and so on down the line. Now, these guys might never have sat in a boat before together. In fact, if you race them against some of the boats that won some of the sub-races, they might lose. But this is a way of picking a boat. Okay, now, I'm just going to leave that picture and come back to it next time so he can come to his class and we'll finish talking about this. Sorry I didn't get to the Markov chains yet, but almost.